we have a triangle, and let's build it this way. So what I'm going to do, I'm going to draw a diagram, and that's the triangle, and in which we have an angle which is theta. Okay, so this angle is fixed, and this is our inclined plane along this side, and for which we have angle theta. So what we are going to do is we are going to launch an object from here, and it will have an angle phi. Okay, so let me draw from here. Let's say this direction we are having angle phi, and this will have a projectile, as we all know, and this will follow like this path and here. Okay, so the problem is that we want to find the range, the distance at which this projectile will fall. So we have a solution. Let's break down the components first. So at this point we have velocity v naught, but it is along that side, so it is also on the x and also in the y. But the problem is that we have angle theta here, we don't have only phi, so we will consider this plane as x plane and this as y. Let me draw a diagram for you. It will be like okay, so we will break the components here. This plane, this is my angle theta, okay, and here this is my angle phi at which we are launching the projectile v naught. So what I'm gonna do, I'm gonna break the components. Let's say this is my x-axis. Okay, I can draw with red pen, and at 90 degree this is my y-axis. We are clear? Yeah, got it. And this is our y-axis, that's 90 degree. Okay, so the velocity component here we will also make it parallel to y-axis. Here the velocity component v naught will equal to, as we know, v naught sine phi, so it is v naught sine phi, and the velocity component which is along that direction is v naught cos phi. Are we clear here? And why I drew this diagram here? So when the projectile will be here, let's say here, so it will have a gravitational pull which we call g. Okay, so it will have g, the gravitational pull. So it will be along two directions. First of all, let's consider that the gravitational pull is along this. This is ground, and it will be perpendicular to the ground, so it will be like this initially. This is g, negative g, as we all know. But at here the projectile is not only facing this, but the g will also be broken down into two components. It will be, the first component will be with parallel to x-axis, and which is the here. Let's draw it here. And the second component will be perpendicular to x-axis, which will be here. Okay, negative g. So one main thing is that it will also make an angle theta here. So let's make a clear picture. Let's say g is here, let's say it is g, and let's say its perpendicular component is here, and it's the negative component here, x-axis, along x-axis. So this angle theta, this will also be theta. Imagine, like, if this angle will get smaller and smaller, this angle will get smaller and smaller, the theta will decrease, the gravitation will only be along the perpendicular of the ground. But if theta is increasing, this angle will also increase, and the components will broken down. So theta is right there, the same angle here is equal to right there. Okay, so this is g. So what we will call this angle? This will be g cos theta. And what will be this component? This will be g sine theta. Okay, we clear here? Okay, so at here x naught is equal to 0, y naught is equal to 0. Okay, so when the projectile will go and it will fall here, the y will also become 0, but x will not become 0, and we have to find this. We also have to find the time when it will fall at this point, and means to say x, we have to find the range here. The maximum range we will calculate later, I will tell you. So we have components of our g. Let's say this is negative, negative, because g is negative along negative y-axis and negative x-axis. So let's write our components. V naught broken down into V naught cos phi, V naught sin phi. So the component which is along along this side, the component which is along this side will face this gravitational pull, which is acceleration, which is equal to negative g sine theta, and and this component, the velocity along the y-axis, will feel this acceleration, which is opposite to that, which is negative g cos theta. Okay, so as we know that we have an equation for which we can find the distance, and it is like this: x minus x naught is equal to initial velocity v naught into time plus half acceleration into t squared. Okay, so we will use this equation for calculating both x and y distance. Okay, so let's start with the x, then we'll go to y. So place this here. Okay, so I think this is much clearer now. Okay, so here we are back with our next page. And yeah, so let's do this. X minus x naught is equal to initial velocity along x, which is, we have written here, initial velocity along x, which is v naught cos phi into time minus, because acceleration is negative, minus g upon 2. So what is g here? G sine theta into t square. Okay, so at initial x not equal to 0, so we will get x equal to v naught cos phi t minus g by 2 sine theta t square. This is our first equation. Let's write it down first. Okay, so let's do this for y. For y, we know that let's come back to the diagram. For y, the initial coordinate is y naught equal to 0, and when the projectile will fall at this point, the y will also equal to 0. So y minus, so for y axis we will use y coordinates. So y minus y naught, which is both are 0. So let's still write it: y minus y naught is equal to initial velocity of y, which is v naught sine phi into t. Okay, minus, because the gravitation, minus g, we have to write the acceleration, minus g, which is cos theta, minus g cos theta upon 2 into t square. So this is 0, as we know, as I discussed here. So this term will come here and become positive here. So let's write it down. This is equal to 0, and this term will come here. It will be like g by 2 cos theta t square is equal to v naught sine phi t. Okay, I think we're done for this, and from here we can see that t can cancel it out. Anything else? No. So we can actually find the value of t from here by doing that. T is equal to v naught sine phi. 2 will come here, 2, g will come down, g, and cos of theta. So that's our value of t. Let's mark it 2. Now what we are going to do, that we will use that value of t that we found in the equation of y coordinates, y axis, and use that value of t in our x axis, so that we can find the range here, range with the time taken the projectile to go from here to here. You get my point? The time taken by a projectile from going here to here is the same time it will go from here to here. The range, the time will be same for both. So we can use this time into this equation. So let's do this. Let's put the value of t in here. So we have x. Let's write it down with black pen. We have x is equal to what we have, v naught cos phi, and t is here, 2 v naught sin phi upon g cos theta. Okay, so the second term minus g by 2 sin theta. Now t the square. Now t square will become 2 square 4 v naught square sin square phi upon g square cos square theta. Are we clear here? We just square that term and put it in here. Now what we can do, we can solve it like, we can cancel it, 2 g with this, anything else, no. Okay, so we are left with, let's just rearrange this statement. X is equal to v naught, no, here v naught into v naught square 2 sin phi cos phi upon g cos theta. Okay, so here we will have 2 v naught square sin square phi into sin theta upon g cos square theta. Okay, I think we are clear till here. Okay, now let's use another page for the clarity. Yeah, right. So what we are gonna do, that we will just solve that question and come to a result. Now from an equation we know that this term, if there is 2 sin theta cos theta, then it becomes sin 2 theta. Okay, so let me write it down. If there is 2 sin theta cos theta, it becomes sine of that angle, of 2 of that angle. Okay, so we will use this term here. Let's do this. What we will get, x equal to v naught square upon, let's write it down here, g cos theta, and this term will become sine 2 theta. Sorry, phi, here phi, sine 2 phi. Okay, so here negative. What we have here, we have let's write the same components as this, v naught square by g, but here cos square theta. Let me see if we can do a shortcut here. Yeah, so we did put our value here. Okay, so v naught square, let's write a 2 with this sine square phi, 2 sine square phi into sine of theta. We clear here? Let's do this for the clarity. Okay, now x is equal to, can we just take that v naught square upon g cos square x, sorry, theta common, like v naught square upon g cos square theta. But remember, here we don't have the square, so we will have to multiply cos theta into this, so it will become sine 2 theta phi cos theta minus what we are left here, 2 sine square phi into sine theta. That's simple, straightforward. Okay, so we are just solving the equation to get a more simplified version of that equation, so that we can find our phi angle, for which we have to find the maximum range. So x equal to v naught square, that's the same equation, g cos square theta. Now pay attention here, Now what we have to do is we have to elaborate the equation more. Now we have to ex expand that term to sine square phi. As we know, now there's a rule in mathematics which says if you have 2 sine square theta or phi in this case, it can become 1 minus cos 2 theta. You can find it on your own, but I can just tell you in clarity that that's a term. If 2 sine square theta we have, then we can convert that into 1 minus cos 2 theta. Okay, so let's put that value of 2 sine square phi here. Sine 2 phi cos theta minus 1 minus cos 2, here we have phi into sine theta. Now what we will do, we will multiply sine theta with this both of these. We will get same terms here, v naught square upon g cos square theta sine 2 phi cos theta. Now here minus sine theta. Now here minus becomes plus. It will become it will become cos 2 phi into sine theta. We can find that this term looks similar to this term, but not same. Similar, like we have sine here, we have cos here, we have 2 phi, and we have theta. But what we have here is we have alternate signs, like we have sine 2 phi cos theta and cos 2 phi sine theta. So according to mathematics, we can also convert that into more simplified way. Let me write something somewhere. It becomes x equal to v naught square upon g cos square theta. Let's write it down separate, minus sine theta. So according to math rule, if we have sine 2 theta sine 2 phi cos theta plus cos 2 phi sine theta, it can be written as sine of addition of both angles, this angle and this angle. Sine of what will it will become 2 phi plus theta. Okay, so that's our answer, that's our maximum range. But still we don't have maximum range, we just have an equation for x if we have same time. Okay, so the time we calculated was for the maximum projectile, like when the projectile will fall and the y becomes 0. And here we have to further find out the value of phi at which we can say that the range can be maximum. So this term here is constant, this is constant, as we have inclined given theta. We can just modify our phi. So we want to make this term as big as possible. So what is the maximum value of sine is equal to 1, and when is 1? When sine, we do sine of 90. Okay, so sine 90 is equal to 1. So here we want to sine 2 phi plus theta equal to 1, and 1 when happens when sine is equal to pi by 2, which is equal to 90 degrees. Okay, so it becomes sine 2 phi plus theta. So here sine cancels sine, what we are left with 2 phi plus theta is equal to pi by 2. Now 2 phi is equal to pi by 2 minus theta. Now phi is equal to pi by 4 minus theta by 2. Now what is pi by 4? As you all know that pi is equal to 180 degree. So pi by 4 will give us 45 degrees. Am I right? So phi will become 45 degree minus theta by 2. So if we use this angle here in phi, this terms becomes maximum, and that's our range, maximum range. So here let's get back to the diagram here. So if we want our projectile to have maximum range, then the phi should be satisfy this equation. 45 minus theta by 2. That's an answer. Thanks for watching the video. I hope this is clear now. Okay, so see you later.